Don't worry, we're going to get into some difficult stuff on QCD and try to make it easy to understand, but right now we need to know some more about the basics first. In the first video we talked about the difference between non-abelian and abelian groups. In this video we want to talk about what makes something a gauge field, and the basic idea here is that we will have 8 independent functions that I'm displaying here, and these functions are going to tell us how the dynamics of the matrix valued field should go. All of these independent functions will work together to make it so that the physics stays the same in any reference frame. Recall that the non-abelian gauge nature of this theory gives us the set of 8 matrices that form the basis of our theory. The gauge part of this story will give us the invariant physics. In the end, we will have something that we will call a matrix-valued gauge field. At every point in space and time, we have a matrix which is made up of the non-abelian group, and it's a 3 by 3 matrix. This matrix, as we will see, will act on a Hilbert space that is 3-dimensional. This physically represents the red, green, and blue color space for our quarks. We will expand more upon this later in later videos, but essentially our matrix-valued gauge field is our gluon field, and the Hilbert space that it acts on is the space of quarks. So now let's get into what makes something a gauge field. Alright, let's talk about what makes something a gauge field. Right, so in the animations we had sort of saw before all of this, what I try to do is I try to allude to the fact that there are going to be these scalar functions that drive the change in our gauge fields. Okay, so it ultimately comes down to these scalar functions to determine the symmetries of a gauge field and how it moves. Okay, so let's start from bare bones. We're going to take a look at Maxwell's equations and then take a look at analogies between Maxwell's equations and how we might be able to make sense of Yang-Mills equations. Okay, so let's go ahead and get started. We're going to start off by proposing the following Lagrangian. Right, so this Lagrangian is this guy right here with this mass term as well. And F mu nu, we've sort of seen that already. We'll come across it again in this video. But now, to find the equations of motion for this Lagrangian, we apply the Euler-Lagrange equations. Okay. So let's look at the first term of the Euler-Lagrange equation here. So with this part right here, right? So we take the derivative of the Lagrangian with respect to the derivative of a nu. And so what we do here, okay, we can split up F mu nu into these 2 bits, and then we have this. This here isn't, there's none of this in here, right? There's no derivative of a mu. So that tells us that we're just working here, or right, we're just working with this term right here. And then we use this relationship right here, okay? This is just Kronecker deltas, right? We have a Kronecker delta on these derivatives, or on these, and a Kronecker delta here as well, right? So that's going to be those guys, that's going to be those guys. All right. When we do that, we get this, right? And then things just start collapsing, right? So alphas are going to become mu's and nu's, right? So this is going to become mu, this is going to become nu, this is going to become mu, this is going to become nu. This is going to be the same thing over here, right? Another way of doing this is we say, okay, this is also equal to just the derivative of these guys, right? So, okay, right, so we're just taking this derivative here of this guy, right? So there's sort of like a break in this equation, or in this derivation, if you will. I don't know why I did it this way, but this is one way of going about it, and we can stop here. The other way we can go about it is we could say, well, we have this guy right here. Here he is, and we're taking the derivative. We're taking the derivative with respect to the derivative of a, or of our a nu. Right, so we just flesh these guys out again. Okay, and now that we have this prescription here, this thing right here, well, we can say that actually we don't really need to do that, right? We can actually just, we say this is 2 mu nu, right? Because we have upper indices, right? So these are going to be the upper indices, right? So upper indice right here. Actually, I'll do this in blue. This is our upper index. Here's our another upper index, right? And when we take the derivative with respect to these guys, well, this is going to get multiplied to here and to here. So it's going to be, and this is a constant, right? This is going to be a constant because we're taking the derivative with, or wait, no, wait. This is going to be the constant, right? Sorry, my bad. This is going to be a constant, right? Because we're taking the derivative with the lower index on these guys, right? We're taking the derivative. And so that happens twice, so we get that 2, right? And then this guy here, this happens twice as well. So we get this 2 right here. All right? So now we can get from here, we just do this multiplication, or we do this, right? 2 and 2 here, that's going to be 4. That should be a plus sign, right? That's, that should be a plus sign, right? Because the minus times the minus, that's going to be a plus sign. Yeah. And so we get 4 mu nu. And then we get this guy right here. All right, so the derivative then, right, so d mu of this, right, so we need to take d mu of this. So that's going to be d mu of this. And what we get then is this right here, right? Just we take the negative out, we get this. We now look at the second term of the Euler-Lagrange equations to get this thing. Right, so now we want to take the derivative of the Lagrangian with respect to a mu, or a nu, and so here's our Lagrangian, and the derivative with respect to a nu, well, these things just contain derivatives of a nu, so we're just looking at this thing now, right? So when we do that, we can effectively ignore this thing, and we get this thing, right? That's just this. This is just squared, right? This is a times a, that's just a squared, and so the 2 cancels out, and we get this term right here. So putting things together, we get this, and then rearranging, we get this. So if we say that our field strength tensor looks like this, then setting the mass of the particle equal to 0, we can get Gauss's law for electromagnetism and the Ampere-Maxwell law for electromagnetism as well. We won't go through their derivations because that's physics 102 or 201, whatever you want to call it. That's not, I'm kind of assuming you know a little bit of physics already, given that we're going through QCD. So essentially, if we have F mu nu to look like this, we can get Gauss's law, we can get Ampere's law, and we can get Maxwell's laws. Right? So we recover the physics from the proposed Lagrangian using the Euler-Lagrange equations. Right? So this was our proposed Lagrangian. Now, here's the thing. This is all to say that the equations of motion or the physics for the electromagnetism comes from the Lagrangian that we proposed. So a gauge field is something that we're now going to add to the Lagrangian that doesn't change the physics. And let's see how this works. Let's consider the following Lagrangian for a massless scalar field. So here we are. So here's our Lagrangian for a massless scalar field. We want to specify massless because mass is actually going to break the symmetry here. So this is for a massless scalar field. M equals 0, right? So we go up here, right? We go up here, and M equals 0, right? So this whole term goes to 0. And this is, again, just our standard definition of F mu nu. We will transform the system in the following way. So we have this guy, right? So A mu and A mu prime, that's the newly transformed A mu, and then it's going to be this guy right here. Now, what's key to understand here, and I don't think many YouTube channels actually teach this very well, is that they just say that this is just like some arbitrary function, right? Take this function, take a derivative, and you'll find out that all the equations of motion are the same. I want to stress here that this function is actually important, right? This function sort of drives what the gauge, or what the gauge potential has to do. Okay, because and we'll see that as we go through. Let's just continue here. So if we do this, if we say that a mu plus the what's this, the divergence or the gradient of this function, right? This again, I want to write this down actually. The gradient of some function lambda is going to drive gauge invariance. So you can almost think of this as like, you have this thing, you have this system in which the equations of motion are rendered invariant. But in order for that to happen, something needs to be working, right? Something needs to be working to keep those equations of motion invariant from anyone's perspective, right? So the things that are working to keep that in check, to sort of keep the physics in check all the time, are these functions, right? That's how I want to picture this, right? I want to picture this as, if you want to keep something at zero, you need to have something involved that does that, right? And so that something is going to be these functions, okay? And you can imagine then sort of flipping this question on its head then and saying, okay, suppose I pick an arbitrary set of functions. Okay, if I pick an arbitrary set of functions, because this is going to be a set of functions when we're talking about QCD, right? This is going to be 8 functions, right? Because we have 8 sort of independent variables, if you will. This is going to be 8 functions. So we're actually going to have a subscript A on this. But so we have these 8 functions sort of playing with each other to make the physics always invariant. Okay? That is the name of the game here for right now. And then later we'll get into actions and where the problems we run into actions. We're going to need to add ghost terms. We're going to need to add gauge fixing terms and all this. But right now, the name of the game is just, we have these functions, they're sort of playing with each other, and they can be intertwined with one another, but they're playing with each other in a way to make the physics invariant under any circumstance. Right? So when we do this, okay, so there's my rant. So we have this thing. Okay, and so let's plug this in, right, to f prime, a prime, a prime. So we just plug these things into prime, right, and we get this. So we recover f mu nu. And then this bit right here, well, for just a scalar function, d mu d nu is equal to d nu d mu, right? So this goes to 0. So f mu nu prime is equal to f mu nu. Right, so whatever we choose for these functions, this happens, right? The newly transformed physics is the same as the old physics, okay? All right, so let's continue. Now let's suppose we add a mass term. So you have these things at play, you have these functions at play, but you throw a little bit of mass into the system now, and what happens? Things don't work. Right, so mass is not jiving well with these 8 functions. So the mass doesn't jive well with these 8 functions because when we plug this thing into these guys, right? So if we just take this mass term, we have this, and then we have to FOIL everything out, right? We have to multiply this with this. We have to multiply this with this, right? We get 2 of these things, and we get this is just a mess. This is a fucking, excuse my French, this is a mess, right? This is so the mass term, this is not invariant. This here does not equal this, right? So this they don't equal each other, right? They don't equal each other. If they did equal each other, this would have to go to 0, right? So 2 A mu d nu would have to equal d mu d nu. That would have to be the case, right? No, wait, no. 2, so no, right? This would have to be the case, right? That minus that would have to be, or plus that would have to be 0, right? So that would have to be 0. And that is not, that's not a condition that we are willing to make, right? So it's not necessarily true. This is not necessarily true. So the mass term sort of, it doesn't jive well with these 8 functions, right? So the mass term is going to break this symmetry. Okay. So if a particle has mass, good luck. The physics is going to be different. Right? So let's bring our notes from the last section. So we have this guy. This was for our electromagnetism. We had this was our field strength tensor. This was our gauge transformation. And so now let's take a look at the non-abelian case. So the non-abelian case, again, we had the reason this is non-abelian again is because these things, these guys here, they came from a mu equaling a mu a t a. There's a secret Einstein sum in there. And so a, right, so these guys here then, well, right, so these guys here are these guys right here, right? Typically we don't write this in this way. Typically you see the a is suppressed, right? But this is how we can write this, right? So we have this thing, which looks like the F mu nu, but then we have this part right here. This is the self-interacting part, right? So we're summing over all of the other fields, all the other gluon fields. We talked about this in the last video, right? So the idea here is that, okay, we have this new interacting term. What does this mean, right? So what does this mean in terms of our gauge transformation? Well, it means that we want to have something that looks like this, but we need it. We need to have it make it look like this now, right? Because these are matrices. This is a matrix valued gauge field, right? So we need these unitary matrices. We're going to propose to have like this, and then these unitary matrices to have like this. And we'll show this later. We'll show. You could plug this in to the Yang-Mills Lagrangian, right? This is our Yang-Mills. This we'll call our Yang-Mills Lagrangian. This here is our Proca-Lagrangian, Proca-Maxwell, whatever you want to call it. Names don't really matter that much. I guess they do, but not if we want to just get the mathematical details here. But the idea here is that, okay, this looks like the same. Like, so we have A's, and then this function here looks something like this, where we have the unchanged derivative as well, right? So A's and the derivative, and we're just sandwiching everything in mu's, or in these these unitary matrices. All right, so okay, so now we can make sense of the bottom right equation, right? Because it takes a very similar form to the gauge transformation in the abelian case, and we'll actually plug this into this in the next video or the video to follow, depending on how I want to order things. But the idea here again is that this is going to jive with this, okay? And we have matrices now playing with each other. Right, we have matrices playing with each other to keep the physics invariant. Okay. Let's recall our matrix valued gauge fields. That's these guys, just to keep those in the forefront of our mind. And so for an infinitesimal transformation now, in the non-abelian case, we will make the choice now of this, right? So here's our gamma, right? So this gamma here it's not exactly the same thing as this gamma, because they're two different theories, right? One is the U1 theory, and then the other one is the non-abelian theory, right? So we have the abelian case, right? The abelian gauge transformation. Now we're going to have non-abelian, where these things have to be matrices. So the inverse is going to be the inverse here, which by the binomial approximation is going to equal this. All right. I'll just write that down, actually. This was from binomial approx, APPROX, right? So that's the binomial approximation. Now let's do some more math here, because everyone here is in love with math, right? So the lambda is a matrix representing the infinitesimal gauge transformation parameters, which is a linear combination of the Lie algebra generators, which those were the Gell-1 matrices. I'm realizing now that I actually haven't presented the Gell-1 matrices, but we don't have to right now, right? We can just say, okay, we have 8 of these matrices, and we're not going to take a look at them right now, but we'll see what the consequences are, and then we'll come back. We'll just take a look at what these matrices look like later to really just solidify our understanding in all of this. So A mu here, so we can write this out, right? So if U is here, here's U, here's inverse of U, right? So we're just doing this right here, right? So right here. Then we're just multiplying things out, right? Multiply things out. And then we can see, okay, again, these things, this is a matrix, right? This is a matrix, right? This is a matrix. Right, so that's a matrix. So we can make sense of this now, right? So that just comes from these guys. And then this guy, let's see here. This guy right here, that's going to be right here, and then G and G, right, and then I and I, that's going to be -1, so we just get this guy right here, which is that guy, and then this guy, then from here to here, we just see, okay, these stay the same, we're just multiplying this to here, and then we have this thing in, when we do, right, so this is just going to be an extra term in lambda squared, right, because we have this times this bit right here. And we're just going to ignore that, because this is an infinitesimal transformation. These are the generators. So these are the matrix generators for U. All right. And so now we can get this guy right here. Okay, right. So let's take this guy, bring it to this side. Right, so that's going to be this bit right here. We're going to call this the change in alpha now. Right, so the change, or not alpha, the change in A. And then we get this guy right here, right? So so this bit right here is right here, and then this bit right here is right here. And then so now putting everything in terms of T, because there's a hidden Einstein sum behind all of these, right? So we just put everything in terms of T. T are the things that are non-abelian, so these things are just functions, right? So we put these in their brackets, okay? Those guys stay the same. And then this guy right here, excuse me. So then we get this, right? Right, because the commutation relationship, right, this guy right here is just this right here and this right here. And then, so we get this, right? So we're just gonna bring it. So this guy right here is right here, and this guy right here is right here. So we're just multiplying both sides by -1, right? But this is just a change between two things, right? So it doesn't really matter if this is negative or not. So this is what the change, right? So here's the change, right? So the change in alpha is given to us by a gradient in these guys, and then we have this term right here. So now we have the gauge generators for the abelian and the non-abelian case. And this is the point that I was trying to get at, right? So we have these functions. They're driving the change in order for the physics to change. And same thing here. They're driving the change in order for the physics to change. The only difference between the non-abelian case is this added term right here. And again, remember, we have hidden Einstein sums everywhere, right? So because A is similar here to here, we need to sum over B and C, right? So we need to sum over B and C. And mu is just a space-time index. All right, so in the non-abelian case then, the lambda terms are a set of 8 space-time dependent functions that serve to parameterize an infinitesimal gauge transformation. The only requirement is that the overall theory remains invariant under any possible choice of these functions. That's what we were talking about. We have these 8 functions now. Right? There are these 8 functions, right? In the abelian case, they're functions. In the non-abelian case, these things are actually matrices. But let's take a look now. Or not matrices. Sorry, we have 8 of them, right? So they're still functions, right? We can actually think of this as a matrix, right? Yes, we can. And I have that later, right? So we can think of this as a matrix because we had this thing right here, right? This doesn't make sense if this is not a matrix and this is a matrix, right? So let's actually take a look at this. So again, these things are driving. These are the generators, right? So the generators are these gamma functions, okay? And that's these guys right here. In the abelian case, we have this. In the non-abelian case, we have this. And then we get our field potentials. Okay. And so what we have now is we have 8 of these. Right? We have 8 of these functions. They're all playing with each other, right? In the abelian case, we just had one, right? It was just one function. This thing is sort of, it's making it so that the physics remains invariant. But here in the non-abelian case, we have 8 of them. They're all sort of interacting with each other to make sure that the physics remains invariant. Okay, and these are just examples, right? These are just an example set of arbitrary functions. These are the functions that I used in the animation to the beginning of this video. I illustrated them, and then I showed you what alpha 5 I think looked like, right? Or not alpha, A5 looked like. But you can, I could have very easily showed you what A6 or 7 or 1 looked like as well. And so that's what we are dealing with, right? So we're dealing with 8 driving functions, if you will. So let's cap off this discussion now by having our workflow made out for us here, right? So we have our generator space-time functions. That's these guys right here, right? So we have 8 of them, and they all get placed into this matrix, right? And then we had 8 of the matrix valued space-time gauge field. Okay, and that's this guy right here. It's very similar. That's very similar structure, right? That's how we can think of this as a matrix. But again, these things are individual functions in their by themselves. And so we use this to generate U, and then we use U to move A. Okay. But what are the equations of motion for our system now, right? So we talked about in the U1 or abelian case, we got Maxwell's equations of motion. In the non-abelian case, we're going to get the Yang-Mills equations of motion. And so what we want to do is we want to take a look at the Yang-Mills equations of motion as well. And if I'm feeling spicy, then I think I will also show how this guy here jives with this. Okay, but right now we can kind of just look at it and be like, they look very similar, so this has to work, right? I'll think about it. But with that being said, make sure to hit that like and subscribe button, and I'll see you guys in the next video.